last time we pretty much talked about specific heat capacity, doing those sort of calculations where, again, as we talked about and as we'll do today in lab, a pretty simple procedure, really just following the temperature change in something like water. We could really figure out, how much heat, for example, was released or absorbed when a reaction takes place. We also talked about that you can, figure out something like the specific heat capacity of a metal by really following the temperature change that you see in water and relating it back to the metal with the understanding of what we talked about, that there is really sort of a kind of perfect transfer of energy. So in our example, I think we did the other day, obviously our metal was a lot hotter than the cold water. So it gave off the energy or released the energy, exothermic in terms of the metal. The water, it was endothermic. It picked up all that heat and energy, which is why we saw the temperature increase in the water. We could use the water information to figure out how much energy that the water absorbed. And as we talked about, that should be the exact same amount of energy that was released by the metal as it went in for a swim. The only difference is the sign that we talked about. So, the amount of energy that was absorbed by the water is equal to, minus the change the sign of the energy that was released by the metal. And that allowed us to use our specific heat equation for the metal to really find the specific heat capacity. Any questions on any of that stuff we did last time? Okay, so to sort of finish up this chapter, we're going to talk about thermochemical equations. And those are really just chemical equations that have a sort of energy element with it. And really, they have a delta H value. So we talked about delta H in this chapter, which is the enthalpy. And these are equations that give you both the equation and the sort of overall enthalpy for a particular reaction. So for example, if we look at this equation here, this is really like the melting of ice. So solid water to liquid water. It has a delta H value of 6.01 kilojoules. When we see an equation like this, we should know that this reaction is exothermic or endothermic. It is actually going to be endothermic. The delta H value is positive, which means it's endothermic. So again, if they give you a delta H value and it's positive, it's an endothermic process. If you get one that's negative, it's an exothermic process. The number is not really important. It's actually just the sign that's important in determining that. And that does make sense. If we think about this, this is ice, right? So you got to put energy in, right? It's got to absorb energy in order for it to melt to liquid water, and it would be an endothermic process. Now, what happens if we sort of did this process the opposite way? We took liquid water back to, say, ice. We basically just took this equation and we flipped it. And now water is our reactant and ice is our product. We can see how it affects the delta H value is the number is exactly the same, but the only thing that changed is the sign. The sign is now negative 6.01, which means in this case, that is a exothermic process, which is what happens when we have liquid water. If you release the heat from the liquid water, they slow down, they no longer can get past each other, and they go into the solid form. So when dealing with these sort of equations where they do give you a delta H value, in some cases, you may need to reverse an equation. You may not need, what's on the reactant side. On that side, you need it on the product side. So how it affects the delta H value is you simply change the sign. So if your original equation was positive and you flip it, the delta H becomes negative, and vice versa. If your original equation was negative for the delta H and you flip it, the delta H will become positive. Again, the actual value for the delta H will be exactly the same. And again, it's the same idea as what we talked about with the metal going into the water. There's sort of a perfect exchange of energy. So when we flip something, it's just looking at another direction. Another very common sort of manipulation of these type of equations is what happens if we don't just need, say, one water in this equation. Maybe we need two. We also can adjust this equation by multiplying the entire equation by 2, which sometimes happens. Sometimes you'll need an equation. And really where this is going to come into play is what we're going to talk about next, which is Hess's Law, where you take a bunch of equations, flip them around, multiply them, kind of put them together to build an overall equation. So for example, if we didn't need that original equation with 2 waters all the way across, we would multiply the 2, and how that affects the delta H value is we would also multiply the delta H value by 2. So we also would just multiply it there by 2. That also means that if you did sort of the opposite approach here, instead of multiplying, let's just say we started with this guy, but we wanted just one of everything. The difference between coming from this equation back to this equation is, for the delta H value, we divide by 2. Yeah. So what we would do is we would technically come across this guy, divide everybody by 2. That would get us back to the original equation. And basically we would also divide the delta H value by 2 if we need to go the opposite way. So those are a few very common ways that we can manipulate these type of equations. If we reverse it, you simply just take the delta H value, change the sign. If you need to multiply by a common number, you need to multiply the entire equation by the common number, and then you would multiply the delta H by that number. And if you need to divide the entire equation by a common number, you would divide the delta H value by a common number. Any questions on any of that? Okay. Yeah. Are you talking about this? Yeah, these are actually the states. So when you look next to a formula, the S means it's in the solid state. The L means it's in a liquid state. And if you see a G, it means it's in the gas state. So those are really just the states. One other one that we commonly see is aqueous, which I think we might have talked about the other day, but that basically means it's like a water environment. Basically, it's a solution, is something dissolved. So those little symbols basically mean what state they're in. And I guess that's a problem jumping to chapter 10 without going through the other chapters first. But in terms of reactants, you always know when you look at an equation that the reactants are always on the left-hand side of the arrow and the products are always on the right-hand side. So that's always the setup when you see the arrow like that. And again, the reactants are obviously just your starting material in the reaction. And obviously the products are what are formed obviously as a result of the reaction. Yeah, you're welcome. Other questions? So where this sort of comes into play is an idea which is referred to as Hess's Law. And Hess's Law is the idea that not all reactions basically occur in like a one-step process. So very common, people think that, we start with our reactants, we get to our products, and that's all like one step. That all happens in one quick step. And it really doesn't. There's a lot of reactions, and most reactions happen in multiple sort of individual steps along the way. So for example, you may have like A plus B goes to C plus D, then C plus D react and make like E plus F. And these are kind of like a one-step, two-step process here. If we wanted to get the overall reaction of what's going on, we could simply just add both of those reaction equations together. And basically, when you add equations together, if there's anything on opposite sides of the arrow that are the same, they essentially cancel each other out. So if we look at the top equation, there's a C on the right, there's a C on the left. Those guys will cancel out when you add them together. You can kind of think of the arrow like an equal sign, like you're subtracting it to the other side if you want. We also see that the D is over there, and there's a D on this side, which they will then cancel out each other. So when you add equations together, anything on opposite sides of the arrow that are the same, they will cancel, or they may just reduce. They may not completely cancel out. If you had like 3 on one side, 2 on the other, it will reduce down to 1 that's left over. So it doesn't have to completely cancel out. They will reduce or cancel. What you're left with after you're done sort of doing all that is everybody on the left-hand side stays on the left-hand side of the arrow. Everybody on the right-hand side of the arrow stays on the right-hand side. So we would bring down A plus B goes to E plus F. And that would be how we would add together a couple of equations. Now, if we had some delta H values for each of these equations, delta H1, delta H2, we could figure out the delta H value of this equation by simply adding both of those together. So we could take the delta H for the first guy plus the delta H for the second guy will give us the delta H reaction, our value for the overall reaction. And that really is what Hess's law is about. It's about taking these kind of individual reactions, manipulate them like we just talked about on the previous slide. Maybe you need to reverse it. Maybe you need to multiply it by a number. Maybe you need to divide it by a number. Maybe you don't have to do anything to that equation until you get everybody sort of on the right side of the arrow, and then you add them together. We could do that and add up all the delta H values, and that will give us the overall delta H value for the reaction. And we could do that because if you remember, energy is a state function. So if you remember way back at the beginning of the chapter, we saw the hikers, right, going up the mountain. And it doesn't matter if you take a direct route, doesn't matter if it takes 20 reactions to get you to the overall product that you're trying to make, or 2. It's only important where you start and where you end. So we can simply add up all these steps. So that's the way you should sort of think about Hess's law. It's kind of like a puzzle. You have a bunch of individual reactions. You got to move them around, manipulate them to get to what you're looking for. So for example, here, if we were to add up this equation here, we would look on the left-hand side and the right-hand side and cancel out anything that could cancel. So in this case, the 2 waters would cancel. And that's pretty much all that's going to cancel. Everything on the left-hand side would stay on the left-hand side. So what we're left with in terms of the left-hand side of the arrow are there. And whatever's left on the right-hand side of the arrow stays here. In this particular case, we didn't really move anything, reverse anything. So we simply would just take both of those delta H values and pretty much add them together. And that is how we get down to here. And what we just did is we basically built the formation of liquid water here. Yes. So hydrogen gas, oxygen gas makes liquid water. And we see the delta H value overall for that process is minus 285.8. which tells us this process is endothermic or exothermic. It is exothermic. It's a negative value for delta H. So again, the overall process of this, when we do those 2 equations or reactions and put them together, is there's a net release of energy into the surroundings as this process occurs. Question on that? All right, so why don't you try one here, I think, yeah. So your goal is to build this equation using these 2 equations here. And you want to figure out what is the delta H value for this reaction. So take a second and see what you come up with. And a really good approach when you're doing these type of problems, because sometimes it can be really confusing sometimes, or those type of lot of equations that maybe you're dealing with. The best thing to do is to look at the equation you're trying to build and just really see if you have everybody on the correct side. That's a really good place to start. So for example, if I was to do this problem, I would first look at carbon here. I see it's on the left-hand side of the arrow. I would go down to my 2 equations and find the only one that has carbon in it, which is the first one. And it is actually on the left-hand side. The other thing you want to make sure of is there's only 1 carbon in the equation we want. There's 1 carbon in the equation we got. So really in this case, we don't have to do anything to it. We could just, if you want, rewrite that equation the way it is. And that means that the delta H value, we didn't really do anything to the equation, will remain the same. The next thing we want to look at perhaps is oxygen. It's on the left-hand side. I see it on the left-hand side here and here. We also could look at the CO2, which is on the right-hand side, and it is on the right-hand side here as well, which means in this particular case, we're kind of lucky. We don't have to really do much to that equation either. We could leave it exactly the same. Again, this is not always the case. You do have to sometimes move them around and rearrange them. And again, because we didn't really do anything to that equation either, the delta H remains the same. That means we're out of equations at this point. If we did everything correctly, we should be able to add those together. We should see that the COs should cancel. And that will then leave us on the left-hand side 1 carbon plus a half O2, and a half O2 is 1, right? 1/2, right? Gives you 1, and CO2. So we now have successfully built the equation that we're looking for in terms of the delta H values for this new reaction. We simply would add these two values together. So we just want to add those two guys together. And if we do that, it looks like it is a negative 393 kilojoules in this particular case. Any questions on that there? Also means this reaction would be exothermic, right? Again, negative delta H. Any questions on it? Yeah. 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 If it wasn't, let's just say, for example, the first equation was like this: CO goes to C plus a half O2, delta H was positive 110. Let's just say that was, you know, the original equation or the top equation. If we needed to reverse it, we would simply reverse the reaction, just change it around, make the reactants the products reactants. And what would happen to the sign is, instead of positive 110, it then would change to negative 110 because we reversed the reaction. So it's what we're talking about on the previous slide. If you turn the reaction around, the delta H value becomes the opposite sign. If you had to multiply, for example, you know, if this one we needed 2, we would multiply everybody here by 2. And then we would also multiply the delta H by 2 as well. So that's what we were talking about on the previous slide. That's really where that will come into play, is these type of problems. Other questions on that? So why don't we try one where you probably need to flip some things around maybe, or move some stuff around. Using these three equations and their delta H values, we want to figure out what is the delta H value for this equation here. So we're looking for what is the delta H value here. All right, take a couple of minutes, see what you come up with. Look and see how you're doing. So again, in these problems, in this case, we actually have 3 different equations we're kind of working with. And in some of these problems, you can get, probably not in this class, you go to the 1A, you'll get a bunch of them, but you could get, like, you know, 5 equations, a ton of different equations. Really, the best approach is to just kind of take the equation you're trying to build and just work with each one individually. So what I mean by that is, clearly here I see I want to end up with a carbon on the left-hand side by itself. If I look up on top, really the only equation that has carbon in it is this first one here. And when I look at it, it is on the left-hand side and it is by itself with one of them. So in that case, the first equation, we really don't have to do anything to. So I'm just going to recopy it, not with all the words there, but I'm just going to call it carbon plus oxygen goes to CO2. And again, because we did not do anything to this equation, the value of the delta H remains the same. That sort of takes care of our first guy. Now I see over here, I'm looking at sulfur, which is also on the left-hand side. I do see sulfur on the left-hand side in this equation here, the second one. The difference is, when I'm done, I don't need 1 sulfur, but I need 2 in this case. That means to this second equation, we need to multiply the entire equation by 2. And when we do that, as we talked about on the other slide, our delta H value then should also get multiplied by 2. So we carry it all the way across. And that's what I'm going to write underneath this equation. So I will have 2 sulfurs plus 2 oxygens, and carrying that 2 to the other side, 2 SO2. My delta H value again now changes. So we're going to take the 296.1, we're going to times it by 2, and it's still going to remain negative. So it's negative 592.2 kilojoules. Again, that's what we get when we multiplied those together. Any questions on that there? Coming to the last thing in the equation we're looking for is the CS2. We see it is actually on the right-hand side. When we look at the equation above, the CS2 is on the left-hand side. So in this case, we need to actually reverse this equation. We need to write it backwards. We actually only need one CS2, and we have one CS2, so we don't have to worry about multiplying by a number or anything like that. But we do need to reverse this reaction. So this last reaction, we need to reverse it. And what that does to our sign here is it goes from negative to positive, right? So we got to reverse the sign when we do that. So reversing that last equation, we get CO2 plus 2SO2 goes to CS2 plus 3O2. Delta H, again, same number, but now it's going to be a positive 1072 kilojoules. When we reverse a reaction, basically everybody on the right-hand side and the left-hand side basically just swap places, obviously. Any questions on that? Now, clearly we are out of equations and we did some manipulation to those equations. So if we did it correctly, we should be in business. So let us see here. If we add up all these equations, we're going to look for anything on opposite sides that could cancel out or reduce down. So we see CO2 on the right, CO2 on the left. Those guys cancel. We see 2SO2 on the left, 2SO2 on the right. Those guys cancel. If we look at this O2, that's 1 O2 plus 2 O2 on the left. That's 3 O2s on the left-hand side, which will cancel out the 3 O2s on the right-hand side. I think that's all the canceling. And we are left with a carbon plus a couple of sulfurs go to CS2, which is what we're looking for in terms of the equation. What's left to do is to take all of our delta H values that we have now changed based on what we did to the equations, and we want to add them all together. So we're going to add all those guys together. And if we do that, it looks like 393.5, which is negative, plus a negative 592.2 equals that, plus a 1072. It looks like overall delta H value here is 86.3 kilojoules in this particular case. This reaction would be endothermic or exothermic. It is endothermic overall. Again, delta H value is positive, again, meaning that endothermic, it will overall absorb energy, this reaction. Any questions on any of that there? So sometimes people get really confused when they try to do Hess's Law. You'll see probably a lot more of it when you go to 1A. There's like a whole chapter on kind of almost that stuff. But really, you just want to keep it simple. Just, start with the equation you're looking for. Make sure everybody's on the correct sides. If not, flip them. Make sure you have the right amount of everybody. And typically, if you do that, everybody else should cancel out correctly, and you should be left with, kind of the right equation. Any questions on Hess's Law or how to do that stuff? All right, so as we talked about, a couple closing remarks on sort of energy and stuff. We did talk about heat. Is that flow of energy from one body to the next. Again, it does sort of flow from hot to cold. We can calculate, sometimes referred to as the change in internal energy. That's what that refers to. That's the change in internal energy. And that is equal to Q, which is heat, and W, which is work. So as we talked about, a lot of times we could use energy, obviously, to do some type of work. And when we talk about change in internal energy, it works the same way as everything else. If it is a positive number, it is an endothermic type process. And if it's a negative number, it is a exothermic type process. All right, I think that's going to wrap it up for chapter 10. There's a few more slides. We're not going to talk about entropy. If you take 1B, you'll talk about entropy in a whole chapter. So we're not going to worry about the couple of slides there. Maybe this is about entropy. And that should wrap up chapter 10. Again, that should be the last stuff that will be on the exam come Monday, right? So again, the exam is Monday through chapter 10. and we'll take it during lab time. Any questions on any of that? Okay, we're going to then roll to chapter 4, which again is not on chapter 1. It will be on exam 1. It'll be on exam 2. Just give me a second here to get it geared up. Okay, we're off to chapter 4, which again is on exam 2. And it covers all kinds of things: elements, atoms, ions. We're going to talk about the structure of the atom. We're going to talk about some important experiments that led to the understanding of the structure of the atom. We'll talk about things like atomic number, mass number, and we'll finish up, I think, talking about sort of the periodic table towards the end of the chapter as well. So a lot of stuff in here. Let's just talk a little bit about formulas of compounds. A reminder, as we talked about, there is a difference in those meanings of a couple of words that we talked about, which is, again, a molecule and a compound. Remember, when we talk about a molecule, that is just really a basic definition of at least 2 or more atoms that have come together. As we talked about, you could have like an element, right? Which obviously, like H2 is an element, but still a molecule because there's 2 atoms of hydrogen. You could have a molecule of water, which is H2O, which is obviously 3 atoms that have come together. But a compound, remember, always contains at least atoms of different elements that are together. So water is considered a compound, is considered a molecule. But again, as we talked about earlier, it is not considered an element because obviously it's 2 different elements that have come together. When we write a chemical formula, it expresses really the number of atoms that are present for each element. We use subscripts to do that. And when we use subscripts in a chemical formula, the number goes to the guy to the left. So if we had like CH4, just like in most things in chemistry, if there is no number written there, it's assumed to be 1. So usually we don't write 1 in chemistry a lot. We just leave it empty. But basically that says that there is 1 carbon present. The 4 here goes to the guy again to the left, which would be the hydrogen. And we would have 4 hydrogen atoms. And if you draw CH4, it looks something like this. And as you can see, 1 carbon atom attached to 4 hydrogen atoms that are there. Water, same thing. The 2 goes for the hydrogen. And again, nothing written there implies that there is 1 oxygen that is present in that chemical formula. There are different types of chemical formulas that we come across. Sometimes chemical formulas, and sometimes they're referred to sometimes as molecular formulas, but chemical formulas can be very basic. Our chemical formulas can give you some information about, the actual compound. For example, if we look at a chemical formula such as this, and a chemical formula such as this, these 2 things are the exact same thing. The guy on the right basically just tells you what's there. Doesn't really give you information maybe about how it's connected. There's 2 carbons, if we count, right? 1 and 2. There's 4 hydrogens, 3 and 4. And there's 2 oxygens, 1 and 2. They're basically the same thing. This guy basically just tells you, hey, that's what's there. This one also tells you what's there, but it does give you actually some information about how everybody's connected together. This, if we drew it, would actually look like this. And you can see from the actual drawing here, we have CH3. These guys are all together, CH3, CO, CO, OH, OH. So this guy, although it also tells you what's present, it does give you some information about how it's actually sort of connected. And sometimes formulas will do that. And sometimes formulas will be like the one on the right, and it's just like, here's what's in there, and it doesn't really give you that information. Any questions on that there? So the rules for writing chemical formulas are as follows. Each atom is represented by its chemical symbol. If you look at the periodic table up there, most symbols are either one letter or two letters. And if it is a one-letter symbol like potassium, which is K, it should be capitalized. If it is a two-letter symbol, it is the first letter that's capitalized. The second one is not. You know, like Fe, which is iron, capital F, lowercase e. Now, there really is importance to that. If you are writing formulas for a symbol and you write CO versus CO, some people may think there's not a big difference between those two things, but there really is. The first one, capital C, lowercase o, is cobalt, which is an element. Capital C, capital O is carbon monoxide, which is something very different than cobalt. So you don't want to always capitalize everything, especially if you're writing the symbols. You know, for a element, should always be the first guy capitalized, second one not. Obviously, some symbols don't really match the names. They come from historical names. Obviously, something like iron, you know, Y is Fe, potassium, Y is K, and stuff like that. For the most part, as we go through these chapters, you should start to have some familiarity with the symbols and what elements they go for. For the most part, if you look on the periodic table, you know, everybody over here, you need to probably know over here, and kind of the first rows and a couple in this area. So the last two rows on the bottom, we don't deal too much with. That row on the bottom where it's kind of like different colors or kind of outlines of element symbols, those are really where they put, depending on when the periodic table was built, you know, where it's kind of just the outline of the symbol. You know, have we decided to give that guy a name, a real name or not? And they're like where we put new elements and those type of things and stuff like that. So on some periodic tables where this particular one goes all the way to like 118, I'm getting old, I think that's what it says. You know, you won't even see some of those elements on other periodic tables depending on when they were made and stuff like that. But you try to get some familiarity with the symbols and the names. It will help you immensely when we get into naming in that chapter and stuff like that. And it's a good idea to have a good handle on that. So here we have H2O, which, as we saw before, 2 hydrogens, 1 oxygen, CO2, 1 carbon, 2 oxygens, and NH3, which is ammonia, 1 nitrogen, and 3 hydrogens for the actual formula. All right, so if we wanted to write the formula for a molecule that contains 6 carbons and 6 hydrogens, we would use carbon, which is C, and put a 6 next to it as a subscript, and a H for hydrogen, and a 6 next to it as a subscript. Not sure where the 6 went, but I'll put it in there. There we go. So it should be C6H6 in that particular case. A compound that contains half as many calcium atoms as there are chlorine atoms. So you can do that very simply. Half of 2 is 1, so calcium and chlorine, CaCl2 would be our answer. And lastly here, a compound that contains equal number of sodium and nitrogen, but 3 times the number of oxygen atoms. So equal sodium, nitrogen, you could do 1 of each, and 3 times that would be 3 oxygens, and that would get us NaNO3, which is sodium nitrate. Now, if we did have a formula, say like Al2SO43, how many aluminum atoms would we have? We would have 2 aluminum. How many sulfur atoms would we have? We would have 3. So in this thing that's in parentheses and you got a number on the outside, you do need to multiply it into both guys here. So that would give us 3 sulfurs, and that would then give us 12 oxygens, or 120, but 12 oxygens there in terms of that. So you sometimes will have formulas that have parentheses. those are what are known as a polyatomic ion, put parentheses, a number on the bottom. It does get distributed, to everybody that's there. Any questions on chemical formulas here? Okay. So what we're going to talk about now is really sort of the important experiments and stuff that led to really the understanding of the atom and its structure. So really a lot of the work towards understanding atoms started way back when there was really this understanding or belief that atoms were these small indivisible particles. You really couldn't destroy them or change them all that much. And early on, sort of philosophers named them atomos, is sort of a forerunner to what we call atoms. A lot of really important work towards the understanding of atoms came about with the development really of what's known as a cathode ray tube, that most everybody believed that most natural materials were either a mixture of pure substances. And as we talked about in chapter 3, pure substances can be either elements or compounds. Like you could have just iron by itself, which is a pure substance. You can have water by itself, which obviously is a compound and a pure substance. There is what is referred to as the law of composition. That means a compound will always have the same composition regardless of where it comes from. So something like water will always have 8 grams of oxygen for every 1 gram of hydrogen. And that is because the formula of water is our H2O. And basically the mass of hydrogen is 1.008 grams. The mass of carbon is 16 grams, which means if you have 2 hydrogens, that's about 2. 16 divided by 2 is about 8 grams of oxygen for every 1 gram of hydrogen that's present. And that always is the case no matter where your water comes from, whether it comes from obviously here, some other country. So early on, understanding of the atom started with a guy by the name of Dalton. And Dalton was not the greatest sort of lecturer. He kept records of the weather every day of his life. He never married, surprisingly. But he did like to go bowling on Thursdays, which is a really good thing to know because that will definitely be on the exams. So don't say Friday because there will be no points for that. So make sure you put Thursday, not Cosmic Sunday or Saturday. But what he really is known for is coming up with really a theory about atoms. Although his theory is not 100% correct in all aspects of it, it did provide a pretty good foundation for, the idea of atoms. So let's talk a little bit about some of his thoughts here about atoms. You do need to be familiar with sort of his atomic theory here. So first off, he said that elements are composed of extremely small particles that are called atoms. He said that all atoms of a given element have the same size, the same mass, and the same chemical properties. And this part of his theory is not so correct, as the existence of isotopes were found. So this part not so correct because of what are known as isotopes. Isotopes are the same element but have different masses. Which means obviously they cannot be identical, even though they are the same element. And as we'll talk about, they basically have different masses because they have different numbers of neutrons present. So that's not so correct. He also said that atoms of one element are different than atoms of others, and that is correct. If you have, an atom of iron, it is different than an atom of carbon or copper. He said that compounds are composed of atoms of more than one element, which is correct, as we've been talking about. A chemical reaction when a chemical reaction basically takes place, the only thing that happens is we get really a rearrangement of the elements. And that is correct. When we have a chemical reaction, the only thing that happens, as we talked about when we talk about energy, is pretty much everybody on the reactant side breaks their bonds, and all those elements reassemble on the product side in some new configurations, which probably gives some new compounds. And that's really the law of conservation of mass. It states that we cannot create nor destroy matter. Basically, what that means is if we start with 6 carbons on the left-hand side of the arrow, we should have 6 carbons somewhere on the right-hand side of the arrow. It may be in different compounds, different elements, and arranged differently, but we won't like lose any carbons along the way. We won't lose any oxygens along the way. That's also why, if you're familiar with balancing chemical equations, why we balance chemical equations, because, you know, if we started with 6 carbons, we should end with 6. We had 2 hydrogens on the left, we should have 2 on the right. But they do rearrange, break bonds, and reform on the other side. So there's really kind of 2 points to Dalton's atomic theory, which is incorrect. As I mentioned earlier, the idea that all elements, atoms of each element, are basically identical to each other. Isotopes do that. And there's also another part of it where it was believed that atoms are sort of indestructible. You can't really change them to some other sort of element. And that's not correct as well. Although that does not happen in a normal chemical reaction, it does happen in nuclear reactions. In nuclear reactions, you can start with one element and you will absolutely end up with a different element when it's all said and done. But in normal chemical reactions, we do have conservation of the elements. Nothing really changes. We don't do anything with nuclear chemistry in here. If you can take 1B, there's a whole chapter on nuclear chemistry where you learn about those things. But in normal chemical reactions, we do have that conservation of the elements, but it is possible to sort of kind of convert one element into another through a nuclear reaction. So here's his idea of the idea of compounds. Again, it's really just a collection of different elements arranged differently. As we talked about, you know, there's so many elements that are up there. Different arrangement, different amounts of them will give you different compounds that have different properties and so forth. Kind of like, again, you know, there's only 26 or so letters there in the alphabet. Different arrangement of those letters give you different words which have different meanings and so forth. So the structure of the atom, we're going to talk about some really important sort of experiments that helped us kind of get there. Based on Dalton's atomic theory, it was believed that really the atom is the basic representation of each element. A series of investigations led to the idea that although atoms are extremely small, they actually do contain an internal structure of even smaller particles. These are what are referred to as subatomic particles. And as you might be familiar with, they are the electrons, the protons, and the neutrons. And as we'll talk about each of these and sort of their discovery, the electrons are negatively charged particles that are found in the atom. Protons are positively charged particles that are found in the atom, and neutrons have no charge that are found in the atom. Now, the discovery of these, you know, sort of revolved around the discovery of others of particles, but really a lot of it all started with sort of the understanding of electrons, the property of electrons, and from that, the sort of discovery of protons. And really not until like 1930s, the discovery of the neutron sort of came about. So let's talk about some of these experiments. We're going to start with the electron. Really, a lot of discovery and a lot of really good research all started with the discovery and the use of what is referred to as a CRT or Crt tube. That is a cathode ray tube. And a cathode ray tube is seen here in this picture, basically. It has basically an electrical plate, a negative side, a positive side. One very important concept in chemistry is, much like life, opposites attract. Yeah. And what that means is if you have like two positive people in life, no, they don't want to be around each other. They're too cheerful. You got two negative people, don't want to be around each other. And it's really, you need like a positive person, a negative person, balance each other out. The same thing kind of works here in chemistry. If something is positively charged, it is attracted to something that is negatively charged. If you get two positive things near each other, they really don't want to be near each other. And if you get two negative things near each other, they don't want to be near each other either. So in this particular case, a CRT tube is really a tube. It's got an electrical plate on each of them. We got a beam of negatively charged particles that would be heading towards the positive plate. Sometimes people will put fluorescent material up here on the end of the tube so you can kind of see where those actual things are hitting. You might be familiar with CRT tubes. Maybe you're not that old yet. Maybe old time TVs. Maybe a relative has one. Maybe you have one. I got one. That's maybe on the floor and it has like a big back to it. Yes. You used to open the back to fix your picture tube and all those things. Those are CRT tubes. Computer monitors that used to have also that like really big back type of thing. Those were CRT monitors. Those are cathode ray tubes. So when your parents used to say, don't sit in front of the TV, it's like shooting you with stuff. Yeah, they were right. They're shooting you with a tube. Obviously, these things don't have them or flat screens or anything like that. But they used to be obviously very popular in our life and using a lot of electronics before obviously more digital things came. So if we have charged particles, which is really important when we use something like an electrical field, which is like positive and negative, if we shoot a particle and it sort of bends up towards the positive side, we would know that particle is a negatively charged particle, right? It would bend up towards the positive side as it's attracted. If you shot a particle through an electrical field and it kind of bent towards the negative side, you would know that that particle is a positive particle. And if you shot particles and it really just went right through the electrical field with no problem, you would also know that it has sort of no charge associated with it. So taking advantage of these subatomic particles that have charges, don't have charges, a lot of experiments use things like electrical fields, magnetic fields, which sort of work the same way, to really take advantage of, kind of moving those beams around and stuff. So as I mentioned, and we don't have to write all that down, it's pretty much what we just talked about. It's a negatively charged thing. It will go and hit the other side in the code. Here's a better picture, probably what I just drew, but again, a lot of electrical fields and magnetic fields, which has a North Pole, South Pole, sort of works very similar. We could really kind of use the trajectory of those particles to help us understand, what is happening with the atom. That is the cathode ray tube, a real one that looks like it. And again, when it's on, this is a fluorescent material that you could kind of see the actual beam and where it's hitting. All right, so one of the really kind of first experiments that really took advantage of the CRT tube was one that was done by Thomson. J.J. Thomson did a lot of work with CRT tubes. And because it was giving off these negatively charged particles, he was able to figure out an important aspect of electrons, which was he was able to figure out the charge to mass of an electron. So Thomson used this CRT tubes to do these experiments. And from that, he was able to figure out the charge to mass of an electron, which is this number down here. It is minus 1.76 times 10 to the 8 coulombs per gram. A C is a coulomb. It's a unit of electrical charge. And gram is obviously a mass. So that is a charge per mass in terms of units. And this was a really good big step forward in understanding some of the properties of electrons. So the first sort of experiment that you should be aware of is Thomson using a Crt tube to figure out the charge to mass of an electron. Sort of following up on sort of Millikan's experiment was really the next sort of step towards understanding electrons. And that was an experiment that was done by a guy named Millikan. Millikan did what is referred to as the oil drop experiment. And basically it is what it sounds like. He took pieces of oil, he took some oil, and he had this sort of compartment here. And there was like a positive side and a negative side. So he had this electrical field set up in this container. He would then sort of shoot his oil droplets in here and get heated up. And the oil droplet, by sort of natural, would want to start to basically drop, right? It's going to start to drop. As it drops, it's going to pick up some charge, right? Some friction and all that good stuff. He was able to basically adjust the electrical field in such a way that the drop basically was suspended. And when it falls to the ground or when it go up, it would obviously just be suspended by sort of dialing in the electrical field. And from that information, he was able to determine the charge on electrons. So this was another very big sort of advancement towards understanding electrons. We have Thomson, who did work with the Crt tube to get the charge to mass. We have Millikan, who was able to get the charge. And if we use both of this information together, we can come up with the actual mass of an electron. So these two experiments sort of go together, as the results were able to be used to really calculate the mass of an actual electron. And that calculation, I think, is on the next page here. We'll take a look. So putting those together, we're able to come up with the actual mass of an electron, which is this number right here, which is 9.09 times 10 to the minus 28 grams. Is that a large number or a small number? That is a really small number. It's like 28 places to the left, right, with a lot of zeros. So that is the mass of an electron. So from these two experiments, we were able to determine the mass of an electron being what's on the bottom. And we also know, again, the electron is negatively charged. Any questions on that so far? Okay. So those two experiments helped us understand electrons, which obviously are negatively charged. So there definitely was a belief that atoms were neutral, which means obviously if they contained electrons that are negatively charged, it was believed that atoms should contain something that is positively charged to balance it out. So that led us to sort of the protons being discovered. But before we got there, there was some steps along the way. So as I said earlier, it was believed that obviously the atoms contained electrons and they were electrically neutral, which meant that we had to have something that's around there that's positive to basically balance it out. Around the turn of the last century, the accepted model for the atom was one that was given by Thomson. And it was basically the idea that the atom was this sphere of positive charge. So within the atom, there's this like sphere of positive charge. And within the atom and the sphere of positive charge, there were electrons that were sort of embedded inside. And it was believed that most of the mass of the atom was these electrons. So the electrons were believed to be really most of the mass of the atom. This was what was referred to as the Plum pudding model. And the Plum pudding model was sort of an early model of the atom. It's basically an English dessert is like pudding with raisins embedded in it. So the guy like, hey, I think that's what an atom looks like. It looks like my dessert. It's this nice sphere of positive charge is spread out, diffused over the whole sphere. We have these electrons that are embedded inside, and it makes up most of the mass of the atom. That is the early model of the atom, which you should be familiar with as well, what it is, what it looked like, sort of the description of it. There's a much prettier picture than what I scribbled on the page, but again, that blue is the positive charge spread out, electrons embedded inside. And this is really sort of an early model of the atom, kind of an accepted model of the atom for a good period of time. But like a lot of things in chemistry, sometimes things has to be readjusted. And there was really a major experiment that sort of occurred that had basically everybody sort of rethinking this idea of the atom being this sort of shape. And that really important experiment was the gold foil experiment. The gold foil experiment was done by a guy named Rutherford with some other people. And it also is pretty much like the title implies. It is, he took pieces of gold foil and he shot at them what are referred to as alpha particles. What are alpha particles? Alpha particles are radioactive particles. They are positively charged radioactive particles, kind of heavy, positively charged radioactive particles. They are essentially helium. They're basically essentially helium atoms up on the periodic table. So what he did is he basically took these alpha particles, he shot at pieces of gold, which are really gold atoms, right? So using that idea, what he expected to happen and what he actually saw happen were really two different things. If we go back to, this model here of the atom, and if this was our atom with that positively charged, really spread out all over it, what he expected when he shot these positively charged, heavy moving and fast moving radioactive particles is when it would come through the atom, it's going to hit something that's positively charged, right? But the positive charge is pretty much spread out over a pretty big distance. So like if you held up a piece of paper and you took a pen and somebody held both sides and you push the pen through the paper, right? It probably would go through, but there would be some deflection as it gets pushed through the paper. And that's what they expected to see. They expected to see these alpha particles kind of come through with some deflection, again, because it's traveling through this really positively charged sort of sphere that has it all separated out. What they actually saw was something very different than that. They actually saw that most of the alpha particles went right through, no problem. They just kind of sailed right through, no problem. The other thing that they saw that was kind of interesting was, in addition to those alpha particles, again, most of them just kind of sailing through, no problem. They saw every so often they would get these alpha particles that basically would bounce off these really large angles. Sometimes they would even head right on back to where they came from, and they had to bounce off at these really, really large angles. First off, if the alpha particles, most of them went through with no problem, what did they hit? Nothing. Yeah, right. If you shoot something and there's nothing there, it's just going to go straight through. If these positively charged alpha particles bounced off at these really large angles every so often, what did they hit? They had to hit something that was very positively charged, right? Things with the same charge don't like each other. So every so often they saw these alpha particles bounce off at these really large angles, which meant they had to hit something very, very positive. And if we think about, that paper example, right? If you took that piece of paper, one paper, and pushed it through, the pen would go through. If you took that same paper and folded it like 7 times or however many times you could fold the paper until that paper is folded to like a piece of paper like that, if I threw a pen at it, what's probably going to happen? It's going to bounce off, right? It's not going to be able to, you're not going to be able to push it through like 7 layers, right? And get through to the other side. It's going to really bounce off. So this was really surprising when they did this experiment that, what they expected to happen, and here's a much prettier picture of the experiment. They have a detector sort of shield where they can see where the beams are. And you can see for the most part, most of the beams just go right on through, no problem. But every so often, we got these guys really bouncing off at these really large angles. We have our alpha particle source coming here. So what this meant was we had to really sort of reevaluate the structure of the atom. And perhaps the Plum pudding model was not really sort of the correct model of the atom. And that's accounted for by most of them going through no problem. Also accounted for, you know, we get these guys bouncing off at these really large angles happening. So what he basically said was, as a result of that, was that the atom was pretty much not the Plum pudding model. And this was not the correct model of the atom, but the atom is a blank screen for dramatic purposes. There we go. So basically what they said was the atom was mostly empty space, like we see here. So that sort of gray area, mostly empty space. That accounted for, again, why the alpha particles went through with no deflection. They also said that it had to contain a dense positive core, and that is what we call now the nucleus, which is this guy right here. So it contains this densely positive core, which is the nucleus. Inside the nucleus, as we'll talk about, that is where we find protons, right, which are positively charged, so that makes sense. By the way, later on, not right now, but later on in the years, it was also found that neutrons are there as well. So we have this dense positive core, which is our nucleus. And what we have is really the electrons outside of the nucleus traveling around. By the way, electrons do not travel in pretty circles. They actually travel randomly about the nucleus. Forget what biology tells you. They don't really travel in pretty circles. They do travel pretty randomly about the nucleus. And there's really no good way to know where an electron is at any particular point in time. The best you could do, as we'll talk about in a later chapter, is there's a really good probability I could find an electron in this location. By the way, is there any attractive force between the electrons that are flying around and the nucleus, which is positively charged? There is, right? Opposites attract. So electrons being negatively charged are flying around. And there is some attraction to the nucleus, which is positively charged, which is why they don't all leave, right? They're kind of attracted to the nucleus, kind of holds them in place, if you will, as they're flying around. The other major difference between really the modern version of the atom, which is what we're talking about here, which is mostly empty space, has a dense positive core, which is the nucleus, is most of the mass of the atom is the nucleus. And we'll talk about why that is. But basically, it is because in the nucleus is the protons, and in the nucleus you find the neutrons. They're both in there together. As we'll talk about probably next time, is that the mass of a proton and a neutron, they are both 1,800 times heavier than any electron. So protons and neutrons are much, much heavier than any electron that's flying around. And that's why we know that most of the mass of the atom is barely made up of the nucleus. Any questions on that?